喂，早晨，有幾位朋友喺度啊？上次 Battery Day 嗰次呢，都係6、7個人，但嗰次仲早，嗰次我記得我係5點起身啊。嗰次 Battery Day 嗱，例牌遲㗎啦，佢哋咁同埋我俾翻條 link 大家呢，原本直播條 link 嘅。咁有位朋友就留低一條，大家去 Tesla 個 channel 度呢，就會見到真正直播條 link 㗎啦。其實大家都睇到嘅。咁但係開始之前佢例遲㗎嘛。咁我都有啲資料俾大家睇嘅，咁有位網友就好好心留咗條 link 俾我，咁大家 in case 去翻原本嘅 channel 度咧都睇到嘅，我而家打出嚟呢條啦，係大家去 Tesla 嗰個官方嗰個頻道度睇會睇到個直播嘅。咁開始之前我一路睇住開始啦，我估佢遲半個鐘嘅，上次都係㗎啦。咁咧，我估下佢今次講啲咩啦？開個 PowerPoint 出嚟先啦。其實呢個 PowerPoint 都準備係真係太忙啦近嚟。咁原本下次嗰條片都係講佢人工智能啲嘢，但係一路都未錄。咁通常我錄影片之前，我會整個 PowerPoint 收集啲資料住嘅，所以可以分享下。都有 research 過佢哋嗰個，即係今日一定會講嘅就係佢封面嗰樣嘢啦，就係佢嗰個 Dojo 嗰個超級電腦。咁佢話佢自己呢 Elon Musk 話佢呢個電腦呢，好大機會係全世界最快嘅電腦咯。全世界最快電腦有幾部嘅，即係一個係日本，一個中國啦。大家應該睇到畫面啦嘛？我及住先，未開始嘅。咁呢個都係我下次 YouTube 影片嘅內容嚟嘅，不過都估下佢今日講啲咩啦。嗱，佢 software 嗰 part 咧，開大聲少少個咪先。我及住有冇開始直播啊？嗱，咁呢個佢呢個咩嚟咧？其實佢software 嗰 part 咧，其實上次自動駕駛日幾年前自動駕駛日咧，嗰陣時 FSD 都未即係宣布 Robot Taxi 嗰個 presentation 啦。佢哋嗰個 AI lead。即係佢哋有個負責人工智能嗰個咧，嗰個之前係 MIT 做教授嘅，好出名嘅。其實我自己上網 search 啲人工智能資料嘅時候咧，係睇到佢啲教學嘅喎 YouTube 度。咁佢之後咧就去咗OpenAI 做 OpenAI 嗰陣時 Elon Musk 係有份㗎嘛嚇 OpenAI。咁 OpenAI 之後就俾 Microsoft 買咗，好似係 Microsoft 買咗。跟住就 Tesla 就退出咗，Elon Musk 就退出咗 OpenAI 嘅，因為佢話佢哋自己開發人工智能。咁同 OpenAI 驚有衝突，咁Elon Musk 就退出咗啦。然之後咧，佢就請咗即係嗰個 Carpathia 嗰個人叫做 Carpathia， 即係而家人就請咗佢過嚟 Tesla 度做人工智能嘅 team lead 啦。有冇佢樣喺度？係啦。咁就佢而家佢人工智能咧，其實具體嚟講係叫 deep learning 嘅。咁 deep learning再具體嚟講咧，呢個係叫 CNN 嘅。咁簡化嚟講，極簡化嚟講咧，就係佢將張相拆解成，即係將啲邊咧每9格，你想象下一粒相好多好 pixel 噶嘛，佢就每9格咁樣拆晒啲橫線、直線、斜線出嚟，拆咗啲線出嚟啦，再將啲線咧組織成一啲特徵嚇，啲特徵佢自己揾嘅。咁例如人類嘅特徵就係有眼睛啊，有鼻。咁呢個 theory 咧，其實同我哋人體嘅眼球一樣噶嘛。其實我哋點解會認到嗰個人呢？其實我哋可能望佢隻眼先。我哋人係傾向望眼先，因為我自己本業係教 marketing 啊嘛。我哋以前做平面設計嘅時候，老師就係話呢，就算你賣件產品都好咧，你最好都放個女 model。其實唔係個 model 男女問題，而係人呢望一張相嘅時候呢，係會望到人嘅眼睛先嘅。呢個人類自然反應。咁所以人工智能一樣咯，佢會揾特徵。咁佢會揾眼啦，佢會透過啲線組織成一個眼出嚟啦，鼻啊，諸如此類咁樣咯。咁然之後咧，佢就透過呢樣辨識到個樣啦。咁其實而家佢哋用緊嘅技術就係呢個技術咯，就不停咁樣，佢會不停咁喺度 scan，好細微。你諗下一張相個 pixel 係而家講緊 4K 啊嘛，影片。係咪1080p 啊嘛？其實係幾千萬粒 pixel 嘅喎一張相，咁佢就每9格係咁 scan 咯。所以佢哋運算嗰個電腦嗰個 power 係要好驚人嘅，因為你講緊你行緊車嘅時候，嗰個鏡頭 1秒係24格啦，冇記錯係嘛？1秒咪24格，有冇人係玩影片嘅？1秒24格啦，先算啦，係咪？咁你24格好多個 pixel 嘅喎，咁你仲要一架車8個鏡頭喎，你8個鏡頭收集翻嚟嘅每1秒24張相，8個鏡頭扯入去分析喎，你諗下嗰個車入邊嗰個 CPU 係幾咁快咯？所以佢之前係揾NVIDIA， 即係而家如果大家有玩電腦有打機就知 NVIDIA 嗰個 GPU 個顯示卡嚇，跟住後期咧，佢哋請埋 Apple 嗰邊嗰個設計晶片嗰個人挖角咗佢過嚟，就幫佢哋架車設計個晶片。咁嗰個車上邊嗰個係有兩個晶片嘅，即係如果一個單咗咧，另外嗰仲可以運算嘅。咁嗰個就係實時啦。架車行緊嘅時候咧，你都會即時運算嘅嚇。咁呢個就係車上面運算好啦。咁但係唔係所有嘢喺個車上面運算嘅。我呢度太多資料嗱，呢啲都係講一個原理啦。我未來嗰條影片都唔會講，我都冇能力講得咁深入。我發現即係好都幾 technical 啊。其實有陣時我哋揾10張，即係平時我哋拍一條 YouTube 片啦，可能我揾咗10個鐘嘅資料，其實係錄到10分鐘嘅影片出嚟嘅啫。即係因為有啲資料都太過 technical，自己消化唔到嚇。咁呢個幾得意，要分享下。咁當初人工智能係點嚟咧？因為有條友佢好殘忍㗎，佢就將嗰啲電極咧插落個貓個腦度嚇，跟住佢發現咧佢哋見到當有橫線直線嘅時候咧，啲貓即係個腦會產生息怒啊。即係所以原來人點樣去理解，即係人去解構翻人係點樣理解呢個世界嘅事物咧？其實我哋係先將啲邊緣界出嚟嘅，例如你而家望到架車，你會望到車嘅表面個邊緣咯，車胎個車身同個背景係棵樹嚟嘅，你係會有能力分翻開噶嘛？係咪分開到前後，所以有立體感啊嘛？嚇咁所以佢透過隻貓咧，見到淨係俾啲直線橫線睇嘅時候，發現咦原來淨係俾啲線睇咧係會產生息怒嘅嚇。咁所以慢慢演變就係話佢就開始所以人工智能就參考翻我哋人嘅原理咧，就係會將啲邊緣界出嚟咯。其實我哋好多我唔知佢今日會講啲嘢，又佢唔排除會解釋啊，唔出奇。但係我聽聞今日嗰個 AI Day 咧，佢冇請媒體，冇請投資者嚟嘅。佢今次呢個目的好明顯就係想刮角一啲全世界最 top 嘅 AI 人員咯。所以佢未必會講一啲咁普通嘅嘢，對佢嚟講普通，佢可能會講啲好 technical 嘅嘢，我唔知。但係佢都會想俾啲學生知嘅，我相信，即係佢要吸納全世界最頂尖嘅人才啊嘛，而家咁就係咁樣咯。咁第一個原理就係話，佢發現到人類係會用邊線啦。其實我哋眼球同埋個相機一樣噶嘛，而家相機嘅快門係我哋眼球個瞳孔打開，吸納咗光線射落嗰個視網膜度調轉咗噶嘛右眼就去咗左邊，其實同相機嘅原理係一樣嘅喎咁呢個第一個原理啦，即係睇邊線。第二個原理就係話，我哋人入邊嗰個腦部嗰個細胞源 neuron， 其實而家你見到左手邊我哋嘅細胞啊咁佢係一層一層去諗嘢嘅，一層一層諗，確實諗乜嘢冇人會知啊，係咪先？嗰粒細胞嚟噶嘛但係大家發現到咧個息路咧係一個咁樣傳過去，經一條嘢咁傳過去嘅，咁所以就衍生咗而家我哋人工智能嗰個網絡咧就係咁樣啦一層一層嘅，即係第一層咧就處理邊線。第二層就將啲邊線再組織成特徵，即係眼啊、耳啊。第三層再將啲特徵組織成一個面孔，跟住 output 啦。佢結果係乜嘢咧？佢係一個車垃圾桶啦，佢一隻狗啊，踩單車嘅人啦，咁樣即係好多個 output 咯。佢要判斷到嗰樣嘢。其實人工智能佢呢個網嘅最終目的就係要 predict 啊嘛，預計未來發生咩事。例如而家係行緊80 km 嘅。再2秒後預計，如果前面嘅車突然間減速咧，佢預計2.5秒咧就會撞後去噶啦。咁佢就要佢得出嘅結果啦然之後佢就要進行判斷咯。個結果就係如果2秒後唔改變嘅話就會撞，佢就要判斷啦，佢就要扭軚咯。佢有幾個 output 可以選擇處理噶嘛？第一個 output 就係油門，第二個剎車，第三個係扭個方向，係嘛？仲有冇其他嘢？應該係呢啲啦跟住就要 output 咯，就係要扭軚剎車咁樣咯。咁呢個就係佢人工智能嘅判斷，所以佢呢度係你想象，如果你會啲線咧係不停咁斬啊，不停咁入緊信息，不停咁輸出緊信息，不停咁入緊信息，跟住扭軚入信息扭軚咁樣咯，即係可能係或者有時唔做嘢啦，就係咁樣處理啦。咁所以佢我哋人就2隻眼咯，而家嘅車就8隻眼。咁可能我估佢其中一個可能會講點解 唔用 LiDAR。嗱，呢個有好留意 Elon Musk 啲新聞先會知我講緊咩嘅啦。LiDAR 即係嗰個光學雷達，咁佢而家用 radar 噶嘛。光學雷達就佢一早就話係戇居嘅，唔用嘅，即係佢嘅口吻得罪咗好多人啦。佢話我哋 SpaceX 火箭我哋都用 LiDAR， 但係個 LiDAR 即係個光學雷達擺落架車度咧係好戇居嘅。佢話咁第一季啦，咁但係有人話喂唔係喎，而家內地同埋有幾間上市公司做到好平喎咁樣，但係 LiDAR 嗰個問題就係你大雨咧，嗰啲水點咧，即係好似新加坡嚟，新加坡成日好大雨，係會影響到嘅咯。其實咁，但係有人預言話 Tesla 最終都要用 LiDAR 平咗之後嚇，但係你冇諗過佢而家係連 radar 都唔用咯，即係聲波係咪叫聲波雷達死啊？即係雷達啦都唔用。咁點解咧？咁佢有解釋過就係話佢會同嗰個 LiDAR 同個鏡頭會有產生衝突啊，成日產生衝突啦。咁佢話如果個 LiDAR 同埋嗰個鏡頭產生衝突嘅時候，咁你 program 嘅時候你信邊個咧？因為咧佢發現到咧，我冇擺落嚟啦，死啦！哇，太多嘢喺度，我唔記得擺落嚟呢度。佢有個例子係阿 Carpuffy 呢個 Carpuffy 啦，就係話佢用 LiDAR 嘅時候發現咧，架車每逢行到去一啲柱等，即係你經過啲橋咧，條橋下邊有條柱等噶嘛。個 LiDAR 每次去到柱等嘅時候咧，佢就覺得有障礙物就會減速喎，突然之間減一減速喎。咁所以佢話每次去到橋等或者咁就會佢即係佢轉噶嘛，個 LiDAR 不停咁轉，佢 detect 到有物體嘛。但係佢又唔係好精準話俾你聽個物體係究竟係擋住架車啊，定喺側邊經過嘅，咁就會有衝突啦。咁所以佢就話，當然你可以花好多時間去調整嗰個雷達同埋個鏡頭去融合，即係令到件事 smooth 啲。但係佢話，與其嘥時間去將兩個咁嘅儀器融合嘅話，不如單純用眼睛咯。咁佢哋個 theory 就係話，喂，其實人類啊，我哋人類去判斷物件不嬲都用眼睛啦。我哋本身都冇 LiDAR，咁我哋都係咁揸車㗎。但係反方啊，即係反方就係話，喂，人梗係越多感應越好㗎啦。咁樣呢個冇對與錯嘅。咁所以而家係好極端嘅兩派。咁 Tesla 應該係全世界冇咁誇張啦。Tesla 同埋另外一間公司 Mobileye 咧 ，Mobileye 就係俾以色列公司就俾 Intel 收購咗嘅。咁 Mobileye 咧佢都佢行唔同技術嘅，因為佢哋 OEM 啊，佢哋唔係自己生產車，佢淨係Mobileye 大家有冇聽過？有冇睇過我之前嗰條片啊？呢個咧就係想做人工智能界嘅 Android 咯。咁 Tesla 係想做 Apple 嘛 ？Apple 嘅意思即係話佢自己開發機、自己開發硬件、自己開發軟件嘛。咁 Mobileye 咧就想做 Android， 即係佢淨係做軟件，然之後就 OEM 俾 Samsung 咯，例如 OEM 俾 Sony 咯，即係你可以用我呢個 system 咯。咁之前咧，蔚來咧 Leo 啊，蔚來就係用 Mobileye 嘅，我唔知而家仲係咪，定係佢唔想講，定係唔想俾人知。因為之前我喺 Mobileye 嗰個 presentation 度咧，我見到蔚來嗰個 logo 係佢個客嚟啊，呢個就係佢哋嗰個創辦人啦，以色列人嚟嘅。咁佢哋話佢哋嗰個無人駕駛喺冇用雷達嘅情況下，喺以色列嗰個喺以色列入邊咁混亂嘅交通都行到咯。佢嘅意思係咁。佢話喺以色列咁混亂嘅交通都行到咧，你世界上邊度都行到啦。佢嘅意思係咁。咁呢個就係 Android 啦。咁即係佢想做自動駕駛嘅 Android。咁呢兩間公司以我所知咧，就係唯一一間公司係完全唔用有唔用雷達技術咯。但係 Tesla 就係即係完全放棄，因為佢要了解間廠，例如蔚來啲車係有裝光達嘅光學雷達嘅，咁佢一定要做個光學雷達嘅軟件俾佢噶嘛。咁所以佢乜都要有咯。佢個意思就係咁啦。好啦。咁所以基本上得兩間公司，以我所知係得兩間公司係可以做到完全冇雷達純用鏡頭，佢哋英文叫 Pure Vision 純視力去做到個駕駛咯。咁啲人覺得好恐怖嘅咁但係而家好難講對與錯啦，有正方亦都有反方咯。咁呢句就係佢嗰句説話嚟嘅，係唔係呢句我 PowerPoint 用嘅，但我未知道，我唔記得咗自己想講咩。係啦，咁佢而家鏡頭最主要 detect 嗰四樣嘢，第一就係路標啦，已經做到噶啦，跟住就係路線啦。咁如果你大家好留意睇嗰啲 FSD 嗰啲片段咧，佢已經好清晰噶啦，紅色線就係邊界，黃色線就係馬路線， 基本上嗰個準程度係99.999嗰啲啦嚇。咁有陣時會有啲古怪嘅情況嘅。佢舉個例子就係話，你有陣時啲馬路係咁樣噶嘛條線嚇，咁所以佢嗰個鏡頭咧係可以 learning 到，即係如果佢可能呢個世界上曾經有10部，而家有幾百萬個 Tesla 不停咁收集咁數據噶嘛，呢個係最厲害之處，冇人會夠佢多車噶啦。咁佢如果當足夠嘅多車行過，即係舉個例子，佢話遇到呢啲路線一啲古怪情況咧，咁佢會感應到架車有問題啦。例如佢自動駕駛嘅時候，個司機見到，咦條路係咁樣嘅，佢突然間收油喎。好啦，收一收油就產生咗一個息路，翻去 Tesla 度知道，有架車行呢個路段嘅時候咧，係會突然間收油嘅。佢感應，佢有數據噶嘛，佢就知道呢個路段有啲古怪嘢咧，係人工智能 handle 唔到嘅。跟住佢會做啲咩咧？然之後你當佢翻去自己嘅 database 有幅圖㗎，佢就翻去自己 database 咧 search 有冇相同嘅喺其他嘅車 cam 入邊有冇相同嘅情況，都係會遇到啲咁古怪嘅路口咧。佢就將嗰啲車 cam 收集到嘅數據咧，全部拉晒佢哋嘅中央系統度先。然之後咧就擺落佢哋個超級電腦啦。等陣會講噶啦，超級電腦就係佢哋而家即佢哋今次邀請信嗰個封面啦。嗰部超級電腦叫 Dojo 啦。Dojo 係日文嚟嘅，道場。我哋華人就會明白個意思係道場就係日本人訓練嘅意思，訓練場啊，就擺入去訓練咧，就會模擬嘅訓練嘅。幅台邊度？呢度係啦。嗱呢度佢遇到問題，然之後咧就收集數據，好多車 cam 嘅數據拉入嚟嚇，擺入嚟 train 係啦，擺入嚟 train 完啦，練習完啦喺道場度。跟住咧就懟翻落架，跟住咧 FSD upgrade，FSD 9.0、9.1啦，而家去到9.2，然之後就 upgrade 佢哋個 system 咯。跟住，所以你架車會點咧？你架車嗱，而家 update 一定要夜晚 WiFi 先 update 到咁架車，你唔會行下 update 咁。咁你嗰晚 update 完之後咧，你架車會突然之間聰明咗嘅，係好神奇嘅。即係你會突然之間一夜之間，你原本行緊呢條路啊，佢日日都有問題嘅。你用自動駕駛，即係去到嗰個路口日日都有問題，突然之間 update 完咧冇問題喎，你會就係咁神奇咯。咁呢個就係佢哋嗰個厲害之處，但係而家中國就話監管啊嘛，即係你 update 個 software 要有監管，因為驚賴嘢。喂，開始未啊？真係例遲半粒鐘過去。好啦，咁個超級電腦係又點樣咧？多炒一炒啲資料先。係啦，佢哋嗰個叫 share 嗱，同埋架車咧，其實。Tesla 嘅車主咧，其實你不停咁訓練緊佢哋嗰個，佢就有個 shadow mode 嘅 shadow mode，即係直譯就影子模式啦。其實佢係做緊乜嘢咧？佢係不停咁樣預測緊你未來3秒發生嘅事。你可以想唔想像？即係話，就算你冇買到 FSD 啊，佢都攞緊你嚟做一個測試啦。嗰邊播緊片頭咯，好快講埋呢個。例如佢 detect 到前邊係有一個。佢 detect 到前邊有個轉彎位嘅，咁佢就預計你轉彎位咧，你應該係行轉右嘅。舉個例子，但係咧，你唔係轉右喎，你轉左喎，咁佢預測就錯咗啦。當佢預測錯嘅時候咧，佢又會收集個數據翻嚟去學習咯。點解我預測會錯咧？佢不停咁分析點解。你咧，因為其實人工智能咧同教小朋友一樣，你要個小朋友學加減數，個前提係你話俾佢聽個答案啱定錯嘛。佢要知道啱定錯，你話俾佢聽啱定錯，佢先學習到啊嘛。咁呢個技術上我哋叫做 supervised learning， 即係監督性，你要俾個答案佢。咁人工智能一樣嘅，佢就不停咁預測啦，你未來係轉右定轉左咧？佢一錯嘅時候，我錯啦，佢就翻去學習咯。其實我哋人類都係咁樣學習噶嘛，你諗真啲。但係佢電腦恐怖啲，諗下人工智能，我哋人咧點樣傳承知識？你諗真啲，我哋一代傳一代噶嘛。愛因斯坦，你諗下，愛因斯坦留嗰啲知識落嚟㗎。但我都學唔到咯 ，sorry， 係咪先？但人工智能好變態喎，人工智能咁就係嘟，佢又傳咗俾下一代噶咯。所以你睇 Black Mirror 啊，你睇如果大家睇 Netflix 嗰啲咧 Black Mirror 啲情節好大機會發生，因為人工智能係唔會退步嘅，佢可以100% 傳承上一代嘅知識。人類咧，你要好勤力，你都未必攞到愛因斯坦5% 嘅知識，明唔明個玩法啊？我呢個人類嘅缺陷，所以人工智能只會越嚟越聰明。所以你問我人工智能會好多人會取代人咧？呢個我覺得係一個必然嘅結果咯。揸車呢件事嗱，我可能會得罪好多揸車嘅人。我之前錄咗條片得罪咗好多揸車嘅人，因為其實揸車係冇必要嘅。你娛樂即係等於騎馬咁樣。以前 係冇必要噶嘛。但係當然你興趣，你而家用為興趣騎馬，你仍然可以騎。但係揸車係浪費時間啊嘛，對我嚟講，我兩隻手擺喺個軚盤度，乜都做唔到喎，係咪？我平時好多我睇好多知識，我揾資料收集嘅時候，我搭車嘅時候喺手機度揾嘅，係嘛？我兩隻手擺喺架車度，乜都做唔到，係咪？我可以睇戲，我可以瞓覺，但係我又要望住前邊，又要揸住睇，即係呢樣嘢係冇必要咯，對人類嚟講。咁所以揸車同埋呢件事成本好高，包括牽涉到而家搭的士好貴。同埋係成個交通係有個破壞性嘅創新，因為我之前影片講過啦，有個人叫 Tony Seba 啊嘛，佢有本書啦，叫 Rethinking Transportation 冇中文嘅。佢話2050年嘅時候咧，佢預計啲車係自動駕駛啦。咁由於自動駕駛嘅成本冇咗，最高嘅成本係咩啊？就係個司機咯。當個司機最高成本冇咗之後咧，你坐無人駕駛嘅車咧就平過你自己擁有一架車啊！咁你日日落街 call 無人駕駛的士咪得咯，你唔使搭巴士，即係你唔使行去搭巴士，你唔使行去搭的士，即係短途啦。我假設，咁你因為平啊嘛，跟住就會產生個 disrupt 啦。同埋而家車咧，好似唔知有70幾% 嘅時間係泊喺度嘅，得3成時間係攞嚟使嘅啫嘛。你諗下，如果你大家有揸車，你諗下自己架車咪大部分時間泊喺度。你夜晚嗰8個鐘照計都泊喺度啦，係咪？你揸車翻工、揸車放工嗰下嗰1-2個鐘嘅啫嘛，大部分時間都係泊喺度嘅。咁係浪費空間啊嘛，佢話。咁你城市你諗下香港有你諗下，區都會有1-2個停車場嘅，即係浪費空間。佢嘅意思就係話，咁所以當你無人駕駛嘅時候，個車嗰個善用率，第一善用地球資源啦。咁停車場少咗，你可以有更多嘅綠化空間咯。咁你攞嚟放太陽能板咯。而家成日都話充電唔方便啊嘛，咁你攞多啲空間嚟放太陽能板咯。咁太陽能板其實呢個技術都 disrupt 咁，因為其實已經發生咗，就係太陽能板其實每度電嗰個成本係平過煤發電嘅啦，只不過你肯唔肯，即係政府肯唔肯去改嘅啫。咁 Tony Seba 已經分享咗個數據啦，係咯。咁呢個就係 disruption， 所以其實 Tesla 咧，佢係同一時間，你應該好難揾到間公司咧係同一時間破壞性創新緊幾個領域嘅。咁第一個係車嘅領域啦，佢生產個工序講緊，即係唔好講人工智能，唔好講電唔電動先。佢生產車嘅方式係破壞緊所有造車產業嘅。你可以想象到啦，其實你福特嗰啲第一架車佢叫 Model T， 就係將亨利福特講緊福特嘅創辦人亨利福特，即係汽車之父嘛。大家有睇過教科書知道，汽車之父佢量產嗰個 model 叫 Model T， 就淘汰咗馬車嘛。嗰個年代佢就係工業化嘅流程啦，再發明咗。唔係用人，即係好多架車，將啲車擺上個生產線。你如果大家睇啲生產工場咧，啲車喺個生產線上面不停咁推過嚟嘅，啲人唔使行架車推過嚟啊嘛。佢就參考咗即係劏啲牛咧，嗰陣時佢參考咗劏牛、劏豬嗰啲工場。原來啲豬咧喺個運輸帶上邊劏啲屠夫咧，就唔需要行啦。佢就咁樣透過咁樣咧去量產人類第一部車，嗰個叫 Model T。嗰 Model T 咧連頂都冇嘅。落雨要擔遮咁嗰時揸車，跟住 Tesla 而家咧就係量產，佢第一部量產真正嘅量產就係 Model 3咯。咁佢嗰個人哋係200幾個零件組裝嘅，你要上落，你要就算你用機械臂都好啦，你要上螺絲，你要焊接，你要黐膠水嗰啲。咁但係佢係一個機器，佢叫 die casting， 中文譯做壓鑄機器，一嘢卜壓出嚟咧，已經慳咗個工序咯，可能慳咗1-2個鐘啦。嗰度一架車慳1-2個鐘，你諗下幾犀利。咁佢自己有提過就話嚟緊德國嗰個工場會更加恐怖嘅，即係佢連嗰個即係佢工廠入邊生產會快啦，同埋佢將架車 deliver 出去嗰個步驟亦都會慳啲咯。所以佢個工場咧係不停咁進步緊嘅。咁呢個係生產工序，即係生產嗰方面嘅一個嘢啦。好啦，第二就係挖礦啊。呢個好少人知，因為佢挖礦咧，其實佢上次 Battery Day 已經講過，佢哋會自己研究挖礦，係全新嘅技術挖礦。咁好多人又係話嗰個鋰電池嗰個 lithium 係咪 lithium 咧？死啦，唔記得咗嗰個。Cobalt 就唔用啦，因為 Cobalt 就係話唔道德啊嘛。Cobalt 就係嗰個喺嗰個剛果共和國度叫啲小朋友刮，咁就係唔係 Tesla 個個有用電池啊 ，Samsung、Apple 都有份㗎啦。你要啲小朋友去刮礦，話唔道德，咁佢減啦。而家仲有少少嘅其實，但係嚟緊都唔用噶啦。咁另外有個就係話，如果佢哋咁樣計咧，根本全球嗰個資源係唔夠嘅。咁 咁第一咧就係唔知上個月咧就已經同咗寧德時代，即係而家佢哋內地供應電池嗰間公司咧就簽咗合約，就話要確保佢哋有電源。咁而家解決咗一個問題啦，嚇。跟住而家第二就話晶片又唔夠啊嘛，即車入邊晶片唔夠啊嘛。咁另外個下電池入邊有其中一個好似係 lithium 啊，唔記得咗邊隻啊，定係 nickel 啊，唔夠資源。咁佢就發明咗一種新嘅技術。咁傳統技術係點做嘅咧？傳統就係喺智利嗰啲礦咧，最傳統嗰種方法咧，因為嗰啲物質咧喺地底度嘅。咁咧，你就要喺上邊放啲水，即係個地面度掘好多窿咧，好大個，你好似個湖面咁樣，唔知你有冇見過湖面？就啲水喺度嘅，跟住咧就靠太陽，因為嗰啲物質咧，你泵出嚟嘅時候咧，嗰啲物質係有雜質啊，純度唔夠高啊。咁點樣整到啲純度高咧？佢好原始嘅方法嘅，就係用有啲水浸住，然之後咧仲用太陽去蒸發咗嗰啲水，剩翻落嚟嗰啲粉啊，就係純嘅物質啦，好似係 lithium 啊，係嘛？有冇人有睇過呢新聞啊？即係咧，如果你有睇過曬鹽咧，啲鹽係點樣整出嚟㗎？你啲海水曬走咗啲水，剩翻落嚟啲鹽，其實個原理差不多啦。最原始嘅方法係極度慢嘅，唔知你要曬1-2年先有一啲 lithium 出嚟，咁就死啦！你咁樣等喺度曬掘又要曬，咁呢個方法係最舊嘅方法嚟㗎嘛？嚇咁之後佢哋Tesla 會研究，佢專利咗啊！最近有專利報告就係佢哋會有其他方法。去更快速去開到啲礦出嚟咯，嚇！咁呢個開礦廠又係一個 disruption 啦。好啦，跟住而家就嚟到呢個自動駕駛咧，就係呢個破壞緊邊個產業咧？就係破壞緊 Uber。嗱，Uber 已經係俾人話破壞性產業嘅嚟㗎啦嘛，但係其實唔係嘅，我覺得，因為 Uber 其實破壞顛覆性創新嘅定義係咩咧？你係要普及你要做多件事普及咧，個成本一定要低。但係其實你而家 call Uber、call Grab 咧，其實你貴過搭的士嘅喎，係咪？你見到 Uber 出咗嚟，的士都仲好多人搭啊，係咪？所以唔係一個破壞性創新咯。嗱，好啦，大家開始睇片啦，咁你
So what we want to show today is that Tesla is much more than an electric and hardware on the inference level, on the training level, and basically, I think arguably the leaders in real-world AI as it applies to the real world. And those of you who have seen the full self-driving beta, I can appreciate the rate at which the Tesla neural net is learning to drive. And so this is a particular application of AI, but I think there are more applications down the road that will make sense, and we'll talk about that later in the presentation. But yeah, we basically want to encourage anyone who is interested in solving real-world AI problems at either the hardware or the software level to join Tesla, or consider joining Tesla. So let's see, we'll start off with Andre. Yep. Great.
I think never mind. Okay, hi everyone. Is my mic on? I hope so.
If not, I can give you mine.
It doesn't sound like it? Okay, hello. Great. Okay, hi everyone. Welcome. My name is Andre, and I lead the vision team here at Tesla Autopilot, and I'm incredibly excited to be here to kick off this section, giving you a technical deep dive into the Autopilot stack and showing you all the under-the-hood components that go into making the car drive all by itself. So we're going to start off with the vision component here. Now, in the vision component, what we're trying to do is we're trying to design a neural network that processes the raw information, which in our case is the 8 cameras that are positioned around the vehicle. And they send us images, and we need to process that in real time into what we call the vector space. And this is a 3-dimensional representation of everything you need for driving. So this is the 3-dimensional positions of lines, edges, curbs, traffic signs, traffic lights, cars, their positions, orientations, depths, velocities, and so on. So here I'm showing a video of, actually, hold on. So here I'm showing the video of the raw inputs that come into the stack, and then the neural network processes that into the vector space. And you are seeing parts of that vector space rendered in the instrument cluster on the car. Now, what I find kind of fascinating about this is that we are effectively building a synthetic animal from the ground up. So the car can be thought of as an animal. It moves around, it senses the environment, and acts autonomously and intelligently. And we are building all of the components from scratch in-house. So we are building, of course, all of the mechanical components of the body, the nervous system, which is all of the electrical components, and for our purposes, the brain of the autopilot, and specifically for this section, the synthetic visual cortex. Now, the biological visual cortex actually has quite intricate structure and a number of areas that organize the information flow of this brain. And so in particular, in your visual cortices, the information hits the light hits the retina, goes through the LGN all the way to the back of your visual cortex, goes through areas V1, V2, V4, the IT, the ventral and the dorsal streams, and the information is organized in a certain layout. And so when we are designing the visual cortex of the car, we also want to design the neural network architecture of how the information flows in the system. So the processing starts in the beginning when light hits our artificial retina, and we are going to process this information with neural networks. Now, I'm going to roughly organize this section chronologically. So starting off with some of the neural networks and what they looked like roughly 4 years ago when I joined the team, and how they have developed over time. So roughly 4 years ago, the car was mostly driving in a single lane, going forward on the highway, and so it had to keep lane and it had to keep distance away from the car in front of us. And at that time, all of processing was only on individual image level. So a single image has to be analyzed by a neural net and make little pieces of the vector space, process that into little pieces of the vector space. So this processing took the following shape. We take a 1280 by 960 input, and this is 12-bit integers streaming in at roughly 36 hertz. Now we're going to process that with a neural network. So we instantiate a feature extractor backbone. In this case, we use residual neural networks. So we have a stem and a number of residual blocks connected in series. Now the specific class of ResNets that we use are RegNets, because RegNets offer a very nice design space for neural networks because they allow you to very nicely trade off latency and accuracy. Now these RegNets give us as an output a number of features at different resolutions and different scales. So in particular, on the very bottom of this feature hierarchy, we have very high resolution information with very low channel counts. And all the way at the top, we have low resolution spatially, but high channel counts. So on the bottom, we have a lot of neurons that are really scrutinizing the detail of the image. And on the top, we have neurons that can see most of the image and a lot of that context, have a lot of that scene context. We then like to process this with feature pyramid networks. In our case, we like to use BiFPNs. And they get to multiple scales to talk to each other effectively and share a lot of information. So for example, if you're a neuron all the way down in the network and you're looking at a small patch and you're not sure if this is a car or not, it definitely helps to know from the top layers that, hey, you are actually in the vanishing point of this highway. And so that helps you disambiguate that this is probably a car. After a BiFPN and a feature fusion across scales, we then go into task-specific heads. So for example, if you are doing object detection, we have a one-stage YOLO-like object detector here where we initialize a raster, and there's a binary bit per position telling you whether or not there's a car there. And then in addition to that, if there is, here's a bunch of other attributes you might be interested in. So the XY with height offset, or any of the other attributes, like what type of a car is this, and so on. So this is for the detection by itself. Now, very quickly we discovered that we don't just want to detect cars, we want to do a large number of tasks. So, for example, we want to do traffic light recognition and detection, a lane prediction, and so on. So very quickly, we converge in this kind of an architectural layout where there's a common shared backbone and then branches off into a number of heads. So we call these, therefore, HydraNets, and these are the heads of the Hydra. Now, this architectural layout has a number of benefits. So number one, because of the feature sharing, we can amortize the forward pass inference in the car at test time. And so this is very efficient to run. Because if we had to have a backbone for every single task, that would be a lot of backbones in the car. Number two, this decouples all of the tasks, so we can individually work on every one task in isolation. And for example, we can uprev any of the data sets or change some of the architecture of the head and so on, and you are not impacting any of the other tasks. And so we don't have to revalidate all the other tasks, which can be expensive. And number 3, because there's this bottleneck here in features, what we do fairly often is that we actually cache these features to disk. And when we are doing these fine-tuning workflows, we only fine-tune from the cached features up and only fine-tune the heads. So most often in terms of our training workflows, we will do an end-to-end training run once in a while where we train everything jointly. Then we cache the features at the multi-scale feature level. And then we fine-tune off of that for a while. And then end-to-end train once again, and so on. So here's the kinds of predictions that we were obtaining, I would say several years ago now, from one of these HydroNets. So again, we are processing individual images. There we go. We are processing just individual image, and we're making a large number of predictions about these images. So for example, here you can see predictions of the stop signs, the stop lines, the edges, the cars, the traffic lights, the curbs here, whether or not the car is parked, all of the static objects like trash cans, cones, and so on, and everything here is coming out of the net, here in this case, out of the HydroNet. So that was all fine and great, but as we worked towards FSD, we quickly found that this is not enough. So where this first started to break was when we started to work on Smart Summon. Here I am showing some of the predictions of only the curb detection task, and I'm showing it now for every one of the cameras. So we'd like to wind our way around the parking lot to find the person who is summoning the car. Now the problem is that you can't just directly drive on image space predictions. You actually need to cast them out and form some kind of a vector space around you. So we attempted to do this using C++ and developed what we called the Occupancy Tracker at the time. So here we see that the curb detections from the images are being stitched up across camera scenes, camera boundaries, and over time. Now there were two major problems, I would say, with this setup. Number 1, we very quickly discovered that tuning the occupancy tracker and all of its hyperparameters was extremely complicated. You don't want to do this explicitly by hand in C++. You want this to be inside a neural network and train that end to end. Number 2, we very quickly discovered that the image space is not the correct output space. You don't want to make predictions in image space. You really want to make it directly in the vector space. So here's a way of illustrating the issue. So here I'm showing on the first row the predictions of our curbs and our lines in red and blue. And they look great in the image, but once you cast them out into the vector space, things start to look really terrible. And we are not going to be able to drive on this. So you see how the predictions are quite bad in vector space. And the reason for this fundamentally is because you need to have an extremely accurate depth per pixel in order to actually do this projection. And so you can imagine just how high of a bar it is to predict that depth so accurately in these tiny, in every single pixel of the image. And also if there's any occluded area where you'd like to make predictions, you will not be able to because it's not an image space concept in that case. So we very quickly the other problems with this, by the way, is also for object detection. If you are only making predictions per camera, then sometimes you will encounter cases like this where a single car actually spans 5 of the 8 cameras. And so if you are making individual predictions, then no single camera sees all of the car. And so obviously you're not going to be able to do a very good job of predicting that whole car. And it's going to be incredibly difficult to fuse these measurements. So we have this intuition that what we'd like to do instead is we'd like to take all of the images and simultaneously feed them into a single neural net and directly output in vector space. Now this is very easily said, much more difficult to actually achieve. But roughly, we want to lay out a neural net in this way, where we process every single image with a backbone, and then we want to somehow fuse them, and we want to re-represent the features from image space features to directly some kind of a vector space features, and then go into the decoding of the head. Now, so there are 2 problems with this. Problem number 1, how do you actually create the neural network components that do this transformation? And you have to make it differentiable so that end-to-end training is possible. And number 2, if you want vector space predictions from your neural net, you need vector space data sets. So just labeling images and so on is not going to get you there. You need vector space labels. We're going to talk a lot more about problem number 2 later in the talk. For now, I want to focus on the neural network architectures, so I'm going to deep dive into problem number 1. So here's the rough problem, right? We're trying to have this bird's eye view prediction instead of image space predictions. So for example, let's focus on a single pixel in the output space in yellow. And this pixel is trying to decide, am I part of a curb or not, as an example. And now, where should the support for this kind of a prediction come from in the image space? Well, we know roughly how the cameras are positioned and their extrinsics and intrinsics, so we can roughly project this point into the camera images. And the evidence for whether or not this is a curb may come from somewhere here in the images. The problem is that this projection is really hard to actually get correct because it is a function of the road surface. The road surface could be sloping up or sloping down, or also there could be other data-dependent issues. For example, there could be an occlusion due to a car. So if there's a car occluding this viewport, this part of the image, then actually you may want to pay attention to a different part of the image, not the part where it projects. And so because this is data-dependent, it's really hard to have a fixed transformation for this component. So in order to solve this issue, we use a transformer to represent this space. And this transformer it uses multi-headed self-attention and blocks of it. In this case, actually, we can get away with even a single block doing a lot of this work. And effectively what this does is you initialize a raster of the size of the output space that you would like, and you tile it with positional encodings with sines and coses in the output space. And then these get encoded with an MLP into a set of query vectors. And then all of the images and their features also emit their own keys and values, and then the query's keys and values feed into the multi-headed self-attention. And so effectively what's happening is that every single image piece is broadcasting in its key what is it a part of. So hey, I'm part of a pillar in roughly this location, and I'm seeing this kind of stuff, and that's in the key. And then every query is something along the lines of, hey, I'm a pixel in the output space at this position, and I'm looking for features of this type. Then the keys and the queries interact multiplicatively, and then the values get pooled accordingly. And so this re-represents the space, and we found this to be very effective for this transformation. So if you do all of the engineering correctly, this again is very easily said, difficult to do. You do all of the engineering correctly. There's one more problem actually before. I'm not sure what's up with the slides. So one more thing, you have to be careful with some of the details here when you are trying to get this to work. So in particular, all of our cars are slightly cockeyed in a slightly different way. And so if you're doing this transformation from image space to the output space, you really need to know what your camera calibration is. And you need to feed that in somehow into the neural net. And so you could definitely just like concatenate the camera calibrations of all of the images and somehow feed them in with an MLP. But actually, we found that we can do much better by transforming all of the images into a synthetic virtual camera using a special rectification transform. So this is what that would look like. We insert a new layer right above the image, rectification layer. It's a function of camera calibration, and it translates all of the images into a virtual common camera. So if you were to average up a lot of repeater images, for example, which face to the back, without doing this, you would get a kind of a blur. But after doing the rectification transformation, you see that the back mirror gets really crisp. So once you do this, this improves the performance quite a bit. So here are some of the results. So on the left, we are seeing what we had before, and on the right, we're now seeing significantly improved predictions coming directly out of the neural net. This is a multi-camera network predicting directly in vector space, and you can see that it's basically night and day. You can actually drive on this. And this took some time and some engineering and incredible work from the AI team to actually get this to work and deploy and make it efficient in the car. This also improved a lot of our object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue. And basically, if you can't predict these cars if you are only seeing a tiny sliver of a car. So your detections are not going to be very good, and their positions are not going to be good. But a multi-camera network does not have an issue. Here's another video from a more nominal sort of situation. And we see that as these cars in this tight space cross camera boundaries, there's a lot of jank that enters into the predictions. And basically, the whole setup just doesn't make sense, especially for very large vehicles like this one. And we can see that the multi-camera networks struggle significantly less with these kinds of predictions. OK, so at this point, we have multi-camera networks, and they're giving predictions directly in vector space. But we are still operating at every single instant in time completely independently. So very quickly, we discovered that there's a large number of predictions we want to make that actually require the video context. And we need to somehow figure out how to feed this into the net. So in particular, is this car parked or not? Is it moving? How fast is it moving? Is it still there, even though it's temporarily occluded? Or for example, if I'm trying to predict the road geometry ahead, it's very helpful to know if the signs or the road markings that I saw 50 meters ago. So we try to develop, we try to insert video modules into our neural network architecture, and this is kind of one of the solutions that we've converged on. So we have the multi-scale features, as we had them from before, and what we are going to now insert is a feature queue module that is going to cache some of these features over time, and then a video module that is going to fuse this information temporally. And then we're going to continue into the heads that do the decoding. Now, I'm going to go into both of these blocks one by one. Also, in addition, notice here that we are also feeding in the kinematics. This is basically the velocity and the acceleration that's telling us about how the car is moving. So not only are we going to keep track of what we're seeing from all the cameras, but also how the car has traveled. So here's the feature queue and the rough layout of it. We are basically concatenating these features over time and the kinematics of how the car has moved and the positional encodings, and that's being concatenated, encoded, and stored in a feature queue. And that's going to be consumed by a video module. Now, there's a few details here, again, to get right. So in particular, with respect to the pop and push mechanisms, and when do you push, and how, and especially when do you push, basically. So here's a cartoon diagram illustrating some of the challenges here. There's going to be the ego car is coming from the bottom and coming up to this intersection here, and then traffic is going to start crossing in front of us, and it's going to temporarily start occluding some of the cars ahead. And then we're going to be stuck at this intersection for a while and just waiting our turn. This is something that happens all the time and is a cartoon representation of some of the challenges here. So number one, with respect to the feature queue and when we want to push into a queue, obviously we'd like to have some kind of a time-based queue where, for example, we enter the features into the queue, say, every 27 milliseconds. And so if a car gets temporarily occluded, then the neural network now has the power to look and reference the memory in time and learn the association that, hey, even though this thing looks occluded right now, there's a record of it in my previous features, and I can use this to still make a detection. So that's kind of like the more obvious one, but the one that we also discovered is necessary in our case is, for example, suppose you're trying to make predictions about the road surface and the road geometry ahead, and you're trying to predict that I'm in a turning lane and the lane next to us is going straight. Then it's really necessary to know about the line markings and the signs, and sometimes they occur a long time ago. And so if you only have a time-based queue, you may forget the features while you're waiting at your red light. So in addition to a time-based queue, we also have a space-based queue. So we push every time the car travels a certain fixed distance. So some of these details actually can matter quite a bit. And so in this case, we have a time-based queue and a space-based queue to cache our features, and that continues into the video module. Now, for the video module, we looked at a number of possibilities of how to fuse this information temporally. So we looked at three-dimensional convolutions, transformers, axial transformers in an effort to try to make them more efficient, recurrent neural networks of a large number of flavors. But the one that we actually like quite a bit as well, and I want to spend some time on, is a spatial recurrent neural network video module. And so what we're doing here is, because of the structure of the problem, we're driving on two-dimensional surfaces, we can actually organize the hidden state into a two-dimensional lattice. And then as the car is driving around, we update only the parts that are near the car and where the car has visibility. So as the car is driving around, we are using the kinematics to integrate the position of the car in the hidden features grid. And we are only updating the RNN at the points where we have that are nearby us, sort of. So here's an example of what that looks like. Here, what I'm going to show you is the car driving around, and we're looking at the hidden state of this RNN. And these are different channels in the hidden state. So you can see that this is after optimization and training this neural net. You can see that some of the channels are keeping track of different aspects of the road, like, for example, the centers of the road, the edges, the lines, the road surface, and so on. Here's another cool video of this. So this is looking at the mean of the first 10 channels in the hidden state for different traversals of different intersections. And all I want you to see basically is that there's cool activity as the recurrent neural network is keeping track of what's happening at any point in time. And you can imagine that we've now given the power to the neural network to actually selectively read and write to this memory. So for example, if there's a car right next to us and is occluding some parts of the road, then now the network has the ability to not write to those locations. But when the car goes away and we have a really good view, then the recurrent neural net can say, okay, we have very clear visibility. We definitely want to write information about what's in that part of space. Here's a few predictions that show what this looks like. So here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. So we're only showing a few of the predictions here just to keep the visualization clean. And yeah, this is done by the spatial RNN. And this is only showing a single clip, a single traversal, but you can imagine there could be multiple trips through here, and basically a number of cars, a number of clips could be collaborating to build this map, basically and effectively an HD map, except it's not in a space of explicit items, it's in a space of features of a recurrent neural network, which is kind of cool. I haven't seen that before. The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where there are two cars over there, and one car is going to drive by and occlude them briefly. So look at what's happening with the single frame and the video predictions as the cars pass in front of us. Yeah, so that makes a lot of sense. So a quick playthrough through what's happening. When both of them are in view, the predictions are roughly equivalent, and you are seeing multiple orange boxes because they're coming from different cameras. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. But the video module knows that there's only a partial, it has the information, and knows that this is not a very easily visible part right now, and doesn't actually take that into account. We also saw significant improvements in our ability to estimate depth, and of course, especially velocity. So here I'm showing a clip from our remove the radar push, where we are seeing the radar depth and velocity in green, and we were trying to match or even surpass, of course, the signal just from video networks alone. And what you're seeing here is in orange, we are seeing a single frame performance, and in blue, we are seeing, again, video modules. And so you see that the quality of depth is much higher. And for velocity, the orange signal, of course, you can't get velocity out of a single frame network, so we just differentiate depth to get that. But the video module actually is basically right on top of the radar signal. And so we found that this worked extremely well for us. So here's putting everything together. This is what our architecture roughly looks like today. So we have raw images feeding on the bottom. They go through a rectification layer to correct for camera calibration and put everything into a common virtual camera. We pass them through RegNets, residual networks, to process them into a number of features at different scales. We fuse the multi-scale information with BiFBN. This goes through a transformer module to re-represent it into the vector space in the output space. This feeds into a feature queue in time or space that gets processed by a video module, like the spatial RNN, and then continues into the branching structure of the HydroNet with trunks and heads for all the different tasks. And so that's the architecture roughly what it looks like today. And on the right, you are seeing some of its predictions sort of visualized both in a top-down vector space and also in images. So definitely, this architecture has definitely complexified from just a very simple image-based single network about 3 or 4 years ago and continues to evolve. It's definitely quite impressive now. There's still opportunities for improvements that the team is actively working on. For example, you'll notice that our fusion of time and space is fairly late in neural network terms. So maybe we can actually do earlier fusion of space or time and do, for example, cost volumes or optical flow-like networks on the bottom. Or for example, our outputs are dense rasters, and it's actually pretty expensive to post-process some of these dense rasters in the car. And of course, we are under very strict latency requirements, so this is not ideal. We actually are looking into all kinds of ways of predicting just the sparse structure of the road, maybe like point by point, or in some other fashion that doesn't require expensive post-processing. But this basically is how you achieve a very nice vector space. And now I believe Ashok is going to talk about how we can run play and control on top of it.
Thank you, Andre. Hi, everyone. My name is Ashok. I lead the planning and controls, auto labeling and simulation teams. So, like Andre mentioned, the vision networks take dense video data and then compress it down into a 3D vector space. The role of the planner now is to consume this vector space and get the car to the destination while maximizing the safety, comfort, and the efficiency of the car. Even back in 2019, our planner was pretty capable driver. It was able to stay in the lanes, make lane changes as necessary, and take exits of the highway. But city driving is much more complicated. Rarely there are structured lane lines. Vehicles do much more free-form driving. Then the car has to respond to all of cut-ins and crossing vehicles and pedestrians doing funny things. What is the key problem in planning? Number one, the action space is very non-convex. And number two, it is high-dimensional. What I mean by non-convex is there can be multiple possible solutions that can be independently good, but getting a globally consistent solution is pretty tricky. So there can be pockets of local minima that the planning can get stuck into. And secondly, the high dimensionality comes because the car needs to plan for the next 10 to 15 seconds. It needs to produce the position, velocities, and acceleration over this entire window. This is a lot of parameters to produce at runtime. Discrete search methods are really great at solving non-convex problems because they are discrete, they don't get stuck in local minima, whereas continuous function optimization can easily get stuck in local minima and produce poor solutions that are not great. On the other hand, for high-dimensional problems, discrete search sucks because it is discrete, it does not use any graded information, so literally it has to go and export each point to know how good it is. Whereas continuous optimization uses gradient-based methods to very quickly go to a good solution. Our solution to this entire problem is to break it down hierarchically. First, use a code search method to crunch down the non-convexity and come up with a convex corridor, and then use continuous optimization techniques to make the final smooth trajectory. Let's see an example of how the search operates. So here, we're trying to do a lane change. In this case, the car needs to do 2 back-to-back lane changes to make the left turn up ahead. For this, the car searches over different maneuvers. So in the first one it searches is lane change that's close by, but the car brakes pretty harshly, so it's pretty uncomfortable. The next maneuver it tries does the lane change a bit late, so it speeds up, goes behind the other car, goes in front of the other cars, and finally does the lane change. But now it risks missing the left turn. We do thousands of such searches in a very short time span. Because these are all physics-based models, these futures are very easy to simulate, and in the end, we have a set of candidates, and we finally choose one based on the optimality conditions of safety, comfort, and easily making the turn. So now the car has chosen this path, and you can see that as the car executes this trajectory, it pretty much matches what we had planned. The cyan plot on the right side here, that one is the actual velocity of the car, and the white line underneath it was the plan. So we are able to plan for 10 seconds here and able to match that when we see in hindsight. So this is a well-made plan. When driving alongside other agents, it's important to not just plan for ourselves, but instead we have to plan for everyone jointly and optimize for the overall scene's traffic flow. In order to do this, what we do is we literally run the autopilot planner on every single relevant object in the scene. Here's an example of why that's necessary. This is an auto corridor. I'll let you watch the video for a second. Yeah, that was autopilot driving in an auto corridor, going around parked cars, cones, and poles. Here, there's a 3D view of the same thing. The oncoming car arrives now, and autopilot slows down a little bit, but then realizes that we cannot yield to them because we don't have any space to our side. But the other car can yield to us instead. So instead of just blindly braking here, autopilot reasons about that car has low enough velocity that they can pull over and should yield to us because we cannot yield to them, and assertively makes progress. A second oncoming car arrives now. This vehicle has higher velocity, and like I said earlier, we literally run the autopilot planner for the other object. So in this case, we run the planner for them. That object's plan now goes around their side's parked cars, and then after they pass the parked cars, goes back to the right side of the road for them. Since we don't know what's in the mind of the driver, we actually have multiple possible futures for this car. Here, one future is shown in red, the other one is shown as green. The green one is a plan that yields to us. But since this object's velocity and acceleration are pretty high, we don't think that this person is going to yield to us, and they are actually going to go around these parked cars. So autopilot decides that, OK, I have space here. This person is definitely going to come, so I'm going to pull over. So as autopilot is pulling over, we notice that that car has chosen to yield to us based on their yaw rate and their acceleration. And autopilot immediately changes its mind and continues to make progress. This is why we need to plan for everyone, because otherwise we wouldn't know that this person is going to go around the other parked cars and come back to their side. If we didn't do this, autopilot would be too timid and would not be a practical self-driving car. So now we saw how the search and planning for other people set up a convex valley. Finally, we do a continuous optimization to produce the final trajectory that the planner needs to take. Here, the gray thing is the convex corridor. And we initialize a spline in heading and acceleration, parameterized over the arc length of the plan. And you can see that the optimization continuously makes fine-grained changes to reduce all of its costs. Some of the costs, for example, are distance from obstacles, traversal time, and comfort. For comfort, you can see that the lateral acceleration plots on the right have nice trapezoidal shapes. It's going to come up for, here on the right side, the green plot. Has a nice trapezoidal shape, and if you record a human trajectory, this is pretty much how it looked like. The lateral jerk is also minimized. So in summary, we do a search for both us and everyone else in the scene. We set up a convex corridor and then optimize for a smooth path. Together, these can do some really neat things like shown above. But driving looks a bit different in other places, like where I grew up from. It's very much more unstructured. Cars and pedestrians cutting each other, harsh braking, honking. It's a crazy world. We can try to scale up these methods, but it's going to be really difficult to efficiently solve this at runtime. What we instead want to do is use learning-based methods to efficiently solve them. And I want to show why this is true. So we're going to go from this complicated problem to a much simpler toy parking problem, but still illustrates the core of the issue. Here, this is a parking lot. The ego car is in blue, and it needs to park in the green parking spot here. So it needs to go around the curbs, the parked cars, and the cones shown in orange here. Let's do the simple baseline. It's a A-star, it's a standard algorithm that uses a lattice space search. And the heuristic here is a distance, the Euclidean distance to the goal. So you can see that it directly shoots towards the goal, but very quickly gets trapped in a local minima. And it backtracks from there, and then searches a different path to try to go around this parked car. Eventually, it makes progress and gets to the goal, but it ends up using 400,000 nodes for making this. Obviously, this is a terrible heuristic. We want to do better than this. So if we added a navigation route to it and has the car to follow the navigation route while being close to the goal, this is what happens. The navigation route helps immediately, but still, when it encounters cones or other obstacles, it basically does the same thing as before, backtracks and then searches a whole new path. And this poor search has no idea that these obstacles exist. It literally has to go there, check if it's in collision, and if it's in collision, back up. The navigation heuristic helped, but still this took 22,000 nodes. We can design more and more of these heuristics to help the search go faster and faster, but it's really tedious and hard to design a globally optimal heuristic. Even if you had a distance function from the cones that guided the search, this would only be effective for the single cone. But what we need is a global value function. So instead, what we want to use is neural networks to give this heuristic for us. The vision networks produce a vector space, and we have cars moving around in it. This basically looks like an Atari game, and it's a multiplayer version. So we can use techniques such as mu0, alpha0, et cetera, that was used to solve Go and other Atari games to solve the same problem. So we're working on neural networks that can produce state and action distributions that can then be plugged into Monte Carlo tree search with various cost functions. Some of the cost functions can be explicit cost functions like distance to collisions, comfort, traversal time, et cetera. But they can also be interventions from the actual manual driving events. We trained such a network for this simple parking problem. So here again, same problem. Let's see how MCTS tree search does. So here you notice that the planner is basically able to, in one shot, make progress towards the goal. To notice that this is not even using a navigation heuristic. Just given the scene, the planner is able to go directly towards the goal. All the other offshoots you're seeing are possible options. It's not choosing any of them, just choosing the option that directly takes it towards the goal. The reason is that the neural network is able to absorb the global context of the scene and then produce a value function that effectively guides it towards the global minima as opposed to getting it stuck in any local minima. So this only takes 288 nodes and several orders of magnitude less than what was done in the A-star with the Euclidean distance heuristic. So this is what a final architecture is going to look like. The vision system is going to crush down the dense video data into a vector space. It's going to be consumed by both an explicit planner and a neural network planner. In addition to this, the network planner can also consume intermediate features of the network. Together, these produce a trajectory distribution, and it can be optimized end-to-end, both with explicit cost functions and human intervention and other imitation data. This then goes into explicit planning function that does whatever is easy for that and produces the final steering and acceleration commands for the car. With that, we need to now explain how we train these networks. And for training these networks, we need large data sets. I invite Andre to speak briefly about manual labeling.
Yeah, so the story of data sets is critical, of course. So far, we've talked only about neural networks, but neural networks only establish an upper bound on your performance. Many of these neural networks, they have hundreds of millions of parameters, and these hundreds of millions of parameters, they have to be set correctly. If you have a bad setting of parameters, it's not going to work. So neural networks are just an upper bound. You also need massive data sets to actually train the correct algorithms inside them. Now, in particular, I mentioned we want data sets directly in the vector space. And so really the question becomes, how can you accumulate, because our networks have hundreds of millions of parameters, how do you accumulate millions and millions of vector space examples that are clean and diverse to actually train these neural networks effectively? Now, so there's a story of data sets and how they've evolved on the side of all of the models and developments that we've achieved. Now, in particular, when I joined roughly 4 years ago, we were working with a third party to obtain a lot of our data sets. Now, unfortunately, we found very quickly that working with a third party to get data sets for something this critical was just not going to cut it. The latency of working with a third party was extremely high, and honestly, the quality was not amazing. And so in the spirit of full vertical integration at Tesla, we brought all of the labeling in-house. And so over time, we've grown more than 1,000-person data labeling org that is full of professional labelers who are working very closely with the engineers. So actually, they're here in the US and co-located with the engineers here in Bay Area as well. And so we work very closely with them. And we also build all of the infrastructure for them from scratch ourselves. So we have a team we are going to meet later today that develops and maintains all of this infrastructure for data labeling. And so here, for example, I'm showing some of the screenshots of some of the latency, throughput, and quality statistics that we maintain about all of the labeling workflows and the individual people involved and all the tasks and how the numbers of labels are growing over time. So we found this to be quite critical, and we're very proud of this. Now, in the beginning, roughly 3 or 4 years ago, most of our labeling was in image space. And so you can imagine that this is taking quite some time to annotate an image like this, and this is what it looked like, where we are sort of drawing polygons and polylines on top of these single individual images. As I mentioned, we need millions of vector space labels, so this is not going to cut it. So very quickly, we graduated to 3-dimensional or 4-dimensional labeling, where we are directly labeling in vector space, not in individual images. So here what I'm showing is a clip, and you are seeing a very small reconstruction. You're about to see a lot more reconstructions soon, but it's a very small reconstruction of the ground plane on which the car drove, and a little bit of the point cloud here that was reconstructed. And what you're seeing here is that the labeler is changing the labels directly in vector space, and then we are reprojecting those changes into camera images. So we're labeling directly in vector space, and this gave us a massive increase in throughput for a lot of our labels because you label once in 3D, and then you get to reproject. But even this, we realized, was actually not going to cut it. Because people and computers have different pros and cons. So people are extremely good at things like semantics, but computers are very good at geometry, reconstruction, triangulation, tracking. And so really for us, it's much more becoming a story of how do humans and computers collaborate to actually create these vector space data sets. And so we're going to now talk about auto labeling, which is some of the infrastructure we've developed for labeling these clips at scale.
Hi again. So even though we have lots of human labelers, the amount of training data needed for training the network significantly outnumbers them. So we try to invest in a massive auto labeling pipeline. Here's an example of how we label a single clip. A clip is an entity that has dense sensor data, like videos, IMU data, GPS, odometry, etc. These can be 45 seconds to a minute long. These can be uploaded by our own engineering cars or from customer cars. We collect these clips and then send them to our servers, where we run a lot of neural networks offline to produce intermediate results, like segmentation masks, depth, point matching, etc. This then goes through a lot of robotics and AI algorithms to produce a final set of labels that can be used to train the networks. One of the first tasks we want to label is the road surface. Typically, we can use splines or meshes to represent the road surface, but those are, because of the topology restrictions, are not differentiable and not amenable to producing this. So what we do instead is in the style of neural radiance fields work from last year, which is quite popular. So we use an implicit representation to represent the road surface. Here, we are querying XY points on the ground and asking for the network to predict the height of the ground surface, along with various semantics such as curbs, lane boundaries, road surface, drivable space, etc. So given a single XY, we get a Z. Together, these make a 3D point. and they can be reprojected into all the camera views. So we make millions of such queries and get lots of points. These points are reprojected into all the camera views. We are showing on the top right here one such camera image with all these points reprojected. Now we can compare this reprojected point with the image space prediction of the segmentations. And jointly optimizing this over all the camera views, both across space and time, produces an excellent reconstruction. Here's an example of how that looks like. So here, this is an optimized road surface that reprojects into the 8 cameras that the car has and across all of time. And you can see how it's consistent across both space and time. So a single car driving through some location can sweep out some patch around the trajectory using this technique. But we don't have to stop there. So here, we collected different clips from the same location, from different cars maybe, and each of them sweeps out some part of their road. Cool thing is we can bring them all together into a single giant optimization. So here, these 16 different trips are organized aligned using various features such as road edges, lane lines. All of them should agree with each other and also agree with all of their image space observations. Together, this provides an effective way to label the road surface, not just where the car drove, but also in other locations that it hasn't driven yet. Again, the point of this is not to just build HD maps or anything like that. It's only to label the clips through these intersections. So we don't have to maintain them forever, as long as the labels are consistent with the videos that they were collected at. Optionally, then humans can come on top of this and clean up any noise or add additional metadata to make it even richer. We don't have to stop at just the road surface. We can also arbitrarily reconstruct 3D static obstacles. Here, this is a reconstructed 3D point cloud from our cameras. The main innovation here is the density of the point cloud. Typically, these points require texture to form associations from one frame to the next frame. But here, we are able to produce these points even on textureless surfaces like the road surface or walls. And this is really useful to annotate arbitrary obstacles that we can see in the world. One more cool advantage of doing all of this on the servers offline is that we have the benefit of hindsight. This is a super useful hack because, say, in the car, the network needs to produce the velocity. It just has to use the historical information and guess what the velocity is. But here, we can look at both the history but also the future and basically cheat and get the correct answer of the kinematics, like velocity, acceleration, etc. One more advantage is that we can have different tracks, but we can stitch them together even through occlusions. Because we know the future, we have future tracks, we can match them and then associate them. So here you can see the pedestrians on the other side of the road are persisted even through multiple occlusions by these cars. This is really important for the planner because the planner needs to know if it saw someone, it still needs to account for them even then they're occluded. So this is a massive advantage. Combining everything together, we can produce these amazing data sets that annotate all of the road texture, all of the static objects, and all of the moving objects, even through occlusions, producing excellent kinematic labels. You can see how the cars turn smoothly, produce really smooth labels. All the pedestrians are consistently tracked. The parked cars have basically zero velocity, so we can also know that they are parked. So this is huge for us. This is one more example of the same thing. You can see how everything is consistent. We want to produce 1 million such labeled clips and train our multicam video networks with such large data set and really crush this problem. We want to get the same view that's consistent that you're seeing here in the car. We started our first exploration of this with the Remove the Radar project. We removed it in a very short time span, I think, within 3 months. In the early days of the network, we noticed, for example, in low visibility conditions, the network can suffer understandably because obviously this truck just dumped a bunch of snow on us and it's really hard to see. But we should still remember that this car was in front of us. But our networks early on did not do this because of the lack of data in such conditions. So what we did, we asked the fleet to produce lots of similar clips. And the fleet responded, it did. So it produces, does it play? Yeah. It produces lots of video clips where shit's falling out of all other vehicles. And we sent this through our auto-labeling pipeline that was able to label 10K clips within a week. This would have taken several months with humans labeling every single clip here. So we did this for 200 different conditions, and we were able to very quickly create large data sets, and that's how we were able to remove this. So once we train the networks with this data, you can see that it's totally working and keeps in memory that this object was there and provides this. So finally, we wanted to actually get a Cybertruck into a data set for the remove the radar. Can you all guess where we got this clip from? I'll give you a moment. Someone said it. Yes, it's rendered. It's our simulation. It was hard for me to tell initially, and if I may say so myself, it looks pretty. It looks very pretty. So yeah, in addition to auto labeling, we also invest heavily in using simulation for labeling our data. So this is the same scene as seen before, but from a different camera angle. So a few things that I wanted to point out, for example, the ground surface. It's not plain asphalt. There are lots of cars and cracks and tar seams. There's some patchwork done on top of it. Vehicles move realistically. The truck is articulated, even goes over the curb and makes a wide turn. The other cars behave smartly. They avoid collisions, go around cars, and also smooth and accelerate smoothly, brake and accelerate smoothly. The car here with the logo on the top is Autopilot. Actually, Autopilot is driving that car, and it's making an unprotected left turn. And since this is simulation, it starts from the vector space. So it has perfect labels. Here we show a few of the labels that we produce. These are vehicle cuboids with kinematics, depth, surface normals, segmentation. But Andre can name a new task that he wants next week, and we can very quickly produce this because we already have the vector space, and we can write the code to produce these labels very, very quickly. So when does simulation help? It helps, number one, when the data is difficult to source. As large as our fleet is, it can still be hard to get some crazy scenes, like this couple and their dog running on the highway while there are other high-speed cars around. This is a pretty rare scene, I'd say, but still can happen, and Autopilot still needs to handle it when it happens. When data is difficult to label, there are hundreds of pedestrians crossing the road. This could be a Manhattan, downtown, people crossing the road. It's going to take several hours for humans to label this clip. And even for automatic labeling algorithms, this is really hard to get the association right, and it can produce like bad velocities. But in simulation, this is trivial because you already have the objects. You just have to like spit out the cuboids and the velocities. And also, finally, when we introduce closed-loop behavior, where the cars needs to be in a determined situation or the data depends on the actions, this is pretty much the only way to get it reliably. All this is great. What's needed to make this happen? Number one, accurate sensor simulation. Again, the point of the simulation is not to just produce pretty pictures. It needs to produce what the camera in the car would see and other sensors would see. So here, we are stepping through different exposure settings of the real camera on the left side and the simulation on the right side. We're able to pretty much match what the real cameras do. In order to do this, we had to model a lot of the properties of the camera in our sensor simulation, starting from sensor noise, motion blur, optical distortions, even headlight transmissions, even like diffraction patterns of the windshield, etc. We don't use this just for the Autopilot software. We also use it to make hardware decisions such as lens design, camera design, sensor placement, even headlight transmission properties. Second, we need to render the visuals in a realistic manner. You cannot have what in the game industry called jaggies. These are aliasing artifacts that are a dead giveaway that this is simulation. We don't want them. So we go through a lot of pains to produce nice spatiotemporal anti-aliasing. We also are working on neural rendering techniques to make this even more realistic. Yeah. In addition, we also use ray tracing to produce realistic lighting and global illumination. Okay, that's the last of the cop cars, I think. We obviously cannot have really just 4 or 5 cars because the network will easily overfit because it knows the sizes. So we need to have realistic assets, like the moose on the road here. We have thousands of assets in our library, and they can wear different shirts and actually can move realistically. So this is really cool. We also have a lot of different locations mapped and created to create these sim environments. We have actually 2,000 miles of road built. And this is almost the length of the roadway from the east coast to the west coast of the United States, which I think is pretty cool. In addition, we have built efficient tooling to build several miles more on a single day for a single artist. But this is just tip of the iceberg. Actually, most of the data that we use to train is created procedurally using algorithms as opposed to artists making these simulation scenarios. So these are all procedurally created roads with lots of parameters such as curvature, varying trees, cones, poles, carts with different velocities, and the interaction produce an endless stream of data for the network. But a lot of this data can be boring because the network may not already get it correct. So what we do is we use also ML-based techniques to basically perturb the network to see where it's failing at and create more data around the failure points of the network. So this is in closed loop trying to make the network performance be better. We don't want to stop there. So actually, we want to recreate any failures that happens to the autopilot in simulation so that we can hold autopilot to the same bar from then on. So here, on the left side, you're seeing a real clip that was collected from a car. It then goes through our auto-labeling pipeline to produce a 3D reconstruction of the scene along with all the moving objects. With this, combined with the original visual information, we recreate the same scene synthetically and create a simulation scenario entirely out of it. So, and then when we replay autopilot on it, autopilot can do entirely new things, and we can form new worlds, new outcomes from the original failure. This is amazing because we really don't want autopilot to fail, and when it fails, we want to capture it and keep it to that bar. Not just that, we can actually take the same approach that we said earlier and take it one step further. We can use neural rendering techniques to make it look even more realistic. So we take the original video clip, recreate a synthetic simulation from it, and then apply neural rendering techniques on top of it, and it produces this, which looks amazing in my opinion, because this one is very realistic and looks almost like it was captured by the actual cameras. This is a result from last night because it was cool and we wanted to present it. But yeah, I'm very excited for what Sim can achieve. But this is not all bullshit because networks trained in the car already use simulation data. We used 300 million images with almost 500 million labels. And we want to crush down all the tasks that are going to come up for the next several months. With that, I invite Milan to explain how we scale these operations and really build a label factory and spit out millions of labels.
All right, thanks, Ashok. Hey, everyone, I'm Milan. I'm responsible for the integration of our neural networks in the car and for most of our neural network training and evaluation infrastructure. And so tonight, I'd just like to start by giving you some perspective into the amount of compute that's needed to power this type of data generation factory. And so in the specific context of the push we went through as a team here a few months ago to get rid of the dependency on the radar sensor for autopilot, we generated over 10 billion labels across 2.5 million clips. And so to do that, we had to scale our huge offline neural networks and our simulation engine across thousands of GPUs and just a little bit shy of 20,000 CPU cores. On top of that, we also included over 2,000 actual autopilot full self-driving computers in the loop with our simulation engine. And that's our smallest compute cluster. So I'd like to give you some idea of what it takes to take our neural networks and move them in the car. And so the two main constraints that we're working under here are mostly latency and frame rate, which are very important for safety, but also to get proper estimates of acceleration and velocity of our surroundings. And so the meat of the problem really is around the AI compiler that we write and extend here within the group that essentially maps the compute operations for my PyTorch model to a set of dedicated and accelerated pieces of hardware. And we do that while figuring out a schedule that's optimized for throughput while working under severe SRAM constraints. And so, by the way, we're not doing that just on one engine, but across two engines on the autopilot computer. And the way we use those engines here at Tesla is such that at any given time, only one of them will actually output control commands to the vehicle, while the other one is used as an extension of compute. But those roles are interchangeable, both at the hardware and software level. So how do we iterate quickly together as a group through these AI development cycles? Well, first, we have been scaling our capacity to evaluate our software and neural network dramatically over the past few years. And today, we're running over 1 million evaluations per week on any code change that the team is producing. And those evaluations run on over 3,000 actual full self-driving computers that are hooked up together in a dedicated cluster. And so on top of this, we've been developing really cool debugging tools. And so here is a video of one of our tools, which is helping developers iterate through the development of neural networks and comparing live the outputs from different revisions of a same neural network model as we're iterating live through video clips. And so last but not least, we've been scaling our neural network training compute dramatically over the past few years. And today, we're barely shy of 10,000 GPUs, which, just to give you some sense, in terms of number of GPU, is more than the top 5 publicly known supercomputers in the world. But that's not enough, and so I'd like to invite Ganesh to talk about the next steps.
Thank you, Milan. My name is Ganesh, and I lead Project Dojo. It's an honor to present this project on behalf of the multidisciplinary Tesla team that is working on this project. As you saw from Milan, there's an insatiable demand for speed as well as capacity for neural network training. And Elon prefetched this, and a few years back, he asked us to design a super fast training computer, and that's how we started Project Dojo. Our goal is to achieve best AI training performance and support all these larger, more complex models that Andre's team is dreaming of, and be power efficient and cost effective at the same time. So we thought about how to build this, and we came up with a distributed compute architecture. After all the training computers out there are distributed computers in one form or the other. They have compute elements in the box out here connected with some kind of network. In this case, it's a two-dimensional network, but it could be any different network. CPU, GPU, accelerators, all of them have compute, little memory, and network. But one thing which is common trend amongst this is it's easy to scale the compute. It's very difficult to scale up bandwidth and extremely difficult to reduce latencies. And you'll see how our design point catered to that, how our philosophy addressed these aspects of traditional limits. For Dojo, we envisioned a large compute plane filled with very robust compute elements backed with large pool of memory and interconnected with very high bandwidth and low latency fabric and in a 2D mesh format. And onto this, for extreme scale, big neural networks will be partitioned and mapped to extract different parallelism, model, graph, data parallelism. And then a neural compiler of ours will exploit spatial and temporal locality such that it can reduce communication footprint to local zones and reduce global communication. And if we do that, our bandwidth utilization can keep scaling with the plane of compute that we desire out here. We wanted to attack this all the way, top to bottom of the stack, and remove any bottlenecks at any of these levels. And let's start this journey in an inside-out fashion, starting with the chip. As I described, chips have compute elements. Our smallest entity of scale is called a training node. And the choice of this node is very important to ensure seamless scaling. If you go too small, it will run fast, but the overheads of synchronization and software will dominate. If you pick it too big, it will have complexities in implementation in the real hardware and ultimately run into memory bottleneck issues. Because we wanted to address latency and bandwidth as our primary optimization point. Let's see how we went about doing this. What we did was we picked the farthest distance a signal could traverse in a very high clock cycle, in this case, 2 gigahertz plus. And we drew a box around it. This is the smallest latency that a signal can traverse, 1 cycle at a very high frequency. And then we filled up the box with wires to the brink. This is the highest bandwidth you can feed the box with. And then we added machine learning compute underneath, and then a large pool of SRAM. And last but not the least, a programmable core to control. And this gave us our high-performance training node. What this is a 64-bit superscalar CPU optimized around matrix multiply units and vector SIMD. It supports floating point 32, bfloat 16, and a new format, CFP8, configurable FP8. And it is backed by 1.25 megabyte of fast ECC-protected SRAM and the low-latency, high-bandwidth fabric that we designed. This might be our smallest entity of scale, but it packs a big punch. More than 1 teraflop of compute in our smallest entity of scale. So let's look at the architecture of this. The computer architects out here may recognize this. This is a pretty capable architecture as soon as you see this. It is a superscalar in-order CPU with 4 wide vector and 2 wide 4 wide scalar and 2 wide vector pipes. We call it in order, although the vector and the scalar pipes can go out of order. But for the purists out there, we still call it in order. And it also has 4-way multi-threading. This increases utilization because we could do compute and data transfers simultaneously. And our custom ISA, which is the instruction set architecture, is fully optimized for machine learning workloads. It has features like transpose, gather, link traversals, broadcast, just to name a few. And even in the physical realm, we made it extremely modular, such that we could start abutting these training nodes in any direction and start forming the compute plane that we envisioned. When we click together 354 of these training nodes, we get our compute array. It's capable of delivering 362 teraflops of machine learning compute. And of course, the high bandwidth fabric that interconnects these. And around this compute array, we surrounded it with high-speed, low-power SerDeses, 576 of them, to enable us to have extreme I/O bandwidth coming out of this chip. Just to give you a comparison point, this is more than 2 times the bandwidth coming out of the state-of-the-art networking switch chips which are out there today. And network switch chips are supposed to be the gold standards for I/O bandwidth. If we put all of it together, we get training-optimized chip, our D1 chip. This chip is manufactured in 7-nanometer technology. It packs 50 billion transistors in a miserly 645 millimeter square. One thing you'll notice, 100% of the area out here is going towards machine learning training and bandwidth. There is no dark silicon. There is no legacy support. This is a pure machine learning machine. And this is the D1 chip in a flip chip BGA package. This was entirely designed by Tesla team internally, all the way from the architecture to GDS out and package. This chip is like a GPU-level compute with a CPU-level flexibility and twice the network chip-level I/O bandwidth. If I were to plot the I/O bandwidth on the vertical scale versus teraflops of compute that is available in the state-of-the-art machine learning chips out there, including some of the startups, you can easily see why our design point excels beyond par. Now that we had this fundamental physical building block, how to design the system around it? Let's see. Since D1 chips can seamlessly connect without any glue to each other, we just started putting them together. We just put 500,000 training nodes together to form our compute plane. This is 1,500 D1 chips seamlessly connected to each other. And then we add Dojo interface processors on each end. This is the host bridge to typical hosts in the data centers. It's connected with PCI Gen 4 on one side with a high bandwidth fabric to our compute plane. The interface processors provide not only the host bridge, but high bandwidth DRAM shared memory for the compute plane. In addition, the interface processors can also allow us to have a higher radix network connection. In order to achieve this compute plane, we had to come up with a new way of integrating these chips together. And this is what we call as a training tile. This is the unit of scale for our system. This is a groundbreaking integration of 25 known good D1 dies onto a fan-out wafer process, tightly integrated such that it preserves the bandwidth between them. The maximum bandwidth is preserved there. And in addition, we generated a connector, a high bandwidth, high density connector that preserves the bandwidth coming out of this training tile. And this tile gives us 9 petaflops of compute with a massive I/O bandwidth coming out of it. This, perhaps, is the biggest organic MCM in the chip industry, multi-chip module. It was not easy to design this. There were no tools that existed. All the tools were croaking. Even our compute cluster couldn't handle it. Our engineers came up with different ways of solving this. They created new methods to make this a reality. Now that we had our compute plane tile with high bandwidth IOs, we had to feed it with power. And here, we came up with a new way of feeding power vertically. We created a custom voltage regulator module that could be reflowed directly onto this fan-out wafer. So what we did out here is we got chip, package, and we brought PCB-level technology of reflow onto this fan-out wafer technology. This is a lot of integration already out here. But we didn't stop here. We integrated the entire electrical, thermal, and mechanical pieces out here to form our training tile fully integrated, interfacing with a 52-volt DC input. It's unprecedented. This is an amazing piece of engineering. Our compute plane is completely orthogonal to power supply and cooling. That makes high bandwidth compute planes possible. What it is a 9 petaflop training tile. This becomes our unit of scale for our system. And this is real. I can't believe I'm holding 9 petaflops out here. And in fact, last week, we got our first functional training tile. And on a limited cooling benchtop setup, we got some networks running. And I was told Andre doesn't believe that we could run networks till we could run one of his creations. Andre, this is MinGPT-2 running on Dojo. Do you believe it? Next up, how to form a compute cluster out of it. By now, you must have realized our modularity story is pretty strong. We just put together some tiles. We just tiled together tiles. A 2x3 tile in a tray makes our training matrix, and 2 trays in a cabinet give 100 petaflops of compute. Did we stop here? No. We just integrated seamlessly. We broke the cabinet walls. We integrated these tiles seamlessly all the way through, preserving the bandwidth. There's no bandwidth divot out here. There's no bandwidth cliffs. All the tiles are seamlessly connected with the same bandwidth. And with this, we have an exapod. This is 1 exaflop of compute in 10 cabinets. It's more than 1 million training nodes that you saw. We paid meticulous attention to that training node, and there are 1 million nodes out here with uniform bandwidth. Not just the hardware, the software aspects are so important to ensure scaling. And not every job requires a huge cluster, so we planned for it right from the get-go. Our compute plane can be subdivided, can be partitioned into units called Dojo processing unit. A DPU consists of 1 or more D1 chips. It also has our interface processor and 1 or more hosts. And this can be scaled up or down as per the needs of any algorithm, any network running on it. What does the user have to do? They have to change their scripts minimally. And this is because of our strong compiler suite. It takes care of fine-grained parallelism and mapping the problems of mapping the neural networks very efficiently onto our compute plane. Our compiler uses multiple techniques to extract parallelism. It can transform the networks to achieve not only fine-grained parallelism using data model graph parallelism techniques, it also can do optimizations to reduce memory footprints. One thing, because of our high bandwidth nature of the fabric is enabled out here, is model parallelism could not have been extended to the same level as what we can. It was limited to chip boundaries. Now we can, because of our high bandwidth, we can extend it to training tiles and beyond. Thus, large networks can be efficiently mapped here at low batch sizes and extract utilization and new levels of performance. In addition, our compiler is capable of handling high-level dynamic control flows like loops, if then else, etc. And our compiler engine is just part of our entire software suite. The stack consists of an extension to PyTorch that ensures the same user-level interfaces that ML scientists are used to. And our compiler generates code on the fly such that it could be reused for subsequent execution. It has a LLVM backend that generates the binary for the hardware. And this ensures we can create optimized code for the hardware without relying on even single line of handwritten kernel. Our driver stack takes care of the multi-host, multi-partitioning that you saw a few slides back. And then we also have profilers and debuggers in our software stack. So with all this, we integrated in a vertical fashion. We broke the traditional barriers to scaling. And that's how we got modularity up and down the stack to add to new levels of performance. To sum it all, this is what it will be. It'll be a fastest AI training computer, 4x the performance at the same cost, 1.3x better performance per watt, that is energy saving, and 5x smaller footprint. This will be Dojo Computer. And we are not done. We are assembling our first cabinets pretty soon, and we have a whole next generation plan already. We are thinking about 10x more with different aspects that we can do, all the way from silicon to the system again. We will have this journey again. We're recruiting heavily for all of these areas. Thank you very much. And next up, Elon will update us on what's beyond our vehicle fleet for AI.
All right. Thank you. Now, unlike Dojo, obviously that was not real. So Dojo is real. The Tesla bot will be real. But basically, if you think about what we're doing right now with the cars, Tesla is arguably the world's biggest robotics company because our cars are like semi-sentient robots on wheels. And with the full self-driving computer, essentially the inference engine on the car, which will keep evolving, obviously, and Dojo, and all the neural nets recognizing the world, understanding how to navigate through the world, it kind of makes sense to put that onto a humanoid form. And we're also quite good at sensors and batteries and actuators. So we think we'll probably have a prototype sometime next year that basically looks like this. And it's intended to be friendly, of course, and navigate through a world built for humans and eliminate dangerous, repetitive, and boring tasks. We're setting it such that it is, at a mechanical level, at a physical level, you can run away from it. And most likely overpower it. So hopefully that doesn't ever happen, but you never know. So it's it'll be a light yeah, anyway, 5 miles an hour. If you can run faster than that, you'll be fine. So yeah, it's around 5'8". Has sort of a screen where the head is for useful information, but it's otherwise basically got the autopilot system in it. So it's got cameras, got 8 cameras, and yeah. Full self-driving computer, and making use of all of the same tools that we use in the car. So, I mean, things that I think that are really hard about having a useful humanoid robot is, can it navigate through the world without being explicitly trained? I mean, without explicit, like, line-by-line instructions. Can you talk to it and say, please pick up that bolt and attach it to the car with that wrench, and it should be able to do that. It should be able to, please go to the store and get me the following groceries, that kind of thing. So, yeah, I think we can do that. And yeah, this I think will be quite profound, because if you say it like, what is the economy? It is, at the foundation, it is labor. So what happens when there is, no shortage of labor? This is why I think long term that there will need to be universal basic income. Yeah. But not right now, because this robot doesn't work. So we just need a minute. So yeah, but I think it's essentially in the future, physical work will be a choice. If you want to do it, you can, but you won't need to do it. And yeah, I think it obviously has profound implications for the economy, because given that the economy at its foundational level is labor, I mean, capital equipment is just distilled labor, then is there any actual limit to the economy? Maybe not. So, yeah. Join our team and help build this. All right, so I think we'll have everyone come back on the stage, and you guys can ask questions if you'd like. Yeah. Maybe try to get the camera angle from there, not from the side. Thanks. All right, cool. So we'll probably turn the lights back on, and yeah, great. So we're happy to answer any questions you have about anything on the software, hardware side, where things are going, and yeah, fire away. We have, because the lights are like interrogation lights, we actually cannot see. There we go. Great. Oh, yeah. All right, cool.
I can just, okay, there we go. First off, I mean, thanks to all the presenters. That was just super cool to see everything. I'm just curious at a high level, and this is kind of a question for really anyone who wants to take it. To what extent are you interested in publishing or open sourcing anything that you do for the future?
Well, I mean, it is fundamentally extremely expensive to create the system, so somehow that has to be paid for. I'm not sure how to pay for it if it's fully open sourced. Yeah, unless people want to work for free. But I should say that this is, if other car companies want to license it and use it in their cars, that would be cool. This is not intended to be just limited to Tesla cars.
Is for the Dojo supercomputer. So did you solve the compiler problem of scaling to these many nodes, or if it is solved, is it only applicable to Dojo? Because I'm doing research in deep learning accelerators, and getting the correct scalability or the distribution, even in one chip, is extremely difficult from the research project's perspective. So I was just curious.
Excuse me, mic for Bill. You want to?
Have we solved the problem? Not yet. Are we confident we will solve the problem? Yes. We have demonstrated networks on prototype hardware now. We have models, performance models showing the scaling. The difficulty is, as you said, how do we keep the localities? If we can do enough model parallel, enough data parallel to keep most of the things local, we just keep scaling. We have to fit the parameters in our working set in our SRAM that we have, and we flow through the pipe. There's plenty of opportunities. Sorry, as we get further scale for further processor nodes, have more local memory trade-offs with bandwidth, we can do more things. But as we see it now, the applications that Tesla has, we see a clear path.
And our modularity story means we can have different ratios, different aspects created out of it. I mean, this is something that we chose for our applications internally.
Sure.
I was just saying that the locality portion of it, given that training is such a soft scaling application, even though you have all this compute and have a high bandwidth interconnect, it could not give you that performance because you're doing computations on limited memory at different locations. So I was that's very curious to me when you said it's solved, because I just jumped onto the opportunity and would love to know more, given that how much you can open source.
Right in there.
Yeah.
Yeah, I guess the proof's in the pudding. So we should have Dojo operational next year, and I think we'll obviously use it for training, video training. I mean, fundamentally, this is about like the primary application initially is we've got vast amounts of video, and how do we train vast amounts of video as efficiently as possible, and also shorten the amount of time. Like if you're trying to train to a task, like just in general, innovation is how many iterations and what is the average progress between each iteration. And so if you can reduce the time between iterations, the rate of improvement is much better. So if it takes like sometimes a couple days for a model to train versus a couple hours, that's a big deal. But the acid test here, and what I've told the Dojo team is, like it's successful if the software team wants to turn off the GPU cluster. But if they want to keep the GPU cluster on, it's not successful. So.
Yeah. Hi, right over here. Love the presentation. Thank you for getting us out here. Loved everything, especially the simulation part of the presentation. I was wondering, it looked very realistic. Are there any plans to maybe expand simulation to other parts of the company in any way?
Mike, too? Hi, I'm Ian Glow. I manage the autopilot simulation team. So as we go down the path to full self-driving, we're going to have to simulate more and more of the vehicle. Currently, we're simulating vehicle dynamics, but we're going to need BMS, we're going to need the MCU, we're going to need every single part of the vehicle integrated. And that actually makes the autopilot simulator really useful for places outside of autopilot. So we want to expand eventually to being a universal simulation platform. But I think before that, we're going to be spinning up a lot of Optimus support. And then a little bit further down the line, we have some rough ideas on potentially how to get the simulation infrastructure and some of the cool things we've built into the hands of people outside of the company.
Optimus is the code name for the Tesla bot.
Oops.
Optimus subprime.
Yeah. Hi, this is Ali Jahanian. Thank you for the great presentation and putting all of these cool things together. Yeah, for a while I have been thinking that the car is already a robot. So why not a humanoid robot? And I'm so happy that today you mentioned that you are going to build such a thing. especially I think that this can give opportunity for ways of putting multi-modality together. For instance, we know that in the example that you showed that there was a dog and with some passengers or running together. The language and symbolic processing can really help for visualizing that. So I was wondering if I could hear a little more about this type of putting modalities together, including language and vision. Because I have been working with, for instance, mini GPT that Andre put out there. And yeah, I didn't hear much about other modalities that's going into the car, or at least in the simulation. Is there any comment that you could tell us?
Well, driving is fundamentally basically almost entirely vision neural nets. Basically, it's running on a biological vision neural net, and what we're doing here is a silicon camera neural net. So there is some amount of audio. You want to hear if there's like emergency vehicles, or I guess converse with the people in the car. If somebody's yelling something at the car, the car needs to understand what that is. So all the things that are necessary for it to be fully autonomous. Yeah. Thank you.
Hi, thank you for all the great work that you've shown. My question is for the team, because the data that was shown seems to be predominantly from the United States that the FSD computer is being trained on. But as it gets rolled out to different countries, which have their own road systems and challenges that come with it, how do you think that it's going to scale? Like I'm assuming like ground up is not a very viable solution. So how does that transfer to different countries?
Well, we actually do train on using data from probably like 50 different countries, but we have to pick. As we're trying to advance full self-driving, we need to pick one country, and since we're located here, we pick the U.S. And then we get a lot of questions like, why not even Canada? I'm like, well, because the roads are a little different in Canada, different enough. And so when trying to solve a hard problem, you want to say like, okay, let's not add additional complexity right now. Let's just solve it for the US, and then we'll extrapolate to the rest of the world. But we do use video from all around the world.
Yeah, I think a lot of what we are building is very country agnostic. Fundamentally, all the computer vision components and so on don't care too much about country-specific sort of features. Different countries have roads, and they have curbs, and they have cars, and everything we're building is fairly general for that.
Yeah, and then the prime directive is don't crash.
Right, and that's true for every country.
Yes, this is the prime directive. Even right now, the car is pretty good at not crashing. And so just basically, whatever it is, don't hit it. Even if it's a UFO that crash landed on the highway, and still don't hit it. You should not need to recognize it in order to not hit it. So that's very important.
And I want to ask that when you do the photometric process, multi-view geometry, how much of an error do you see? Is it like 1 millimeter, 1 centimeter? So if it's not confidential.
Sorry, is the question, what is the resolution?
What's the difference between the synthetic? Sure. What is the difference between the synthetically created geometry to the actual geometry?
Yeah, it's usually within a couple centimeters, 3 or 4 centimeters. That's the standard deviation.
With different kind of modalities to bring down that error.
We primarily try to find scalable ways to label. In some occasions, we use other sensors to help benchmark, but we primarily try to use cameras for this system.
Okay, thanks.
Yeah, I mean, I think we want to aim for the car to be positioned accurately to the sort of centimeter level, you know, something on that order.
Obviously, it will depend on distance. Like close by things can be much more accurate than farther away things, and they would matter less because the car doesn't have to make decisions much farther away. And as it comes close, it will become more and more accurate.
Exactly. A lot of questions.
Thanks, everybody. My question has to do with sort of AI and manufacturing. It's been a while since we've heard about the alien dreadnought concept. Is the humanoid that's behind you guys, is that kind of brought out of the production hell timeline and saying that humans are underrated in that process?
Well, sometimes like something that I say is taken to too much of an extreme. There are parts of the Tesla system that are almost completely automated, and then there are some parts that are almost completely manual. If you were to walk through the whole production system, you would see a very wide range from, like I said, fully automatic to almost completely manual. But the vast majority, most of it is already automated. And then with some of the design architecture changes, like going to large aluminum high-pressure die-cast components, we can take the entire rear third of the car and cast it as a single piece. And now we're going to do the front third of the car as a single piece. So the body line drops by like 60 to 70% in size. But yeah, the robot is not prompted by specifically by manufacturing needs. It's just that we're just obviously making the pieces that are needed for a useful humanoid robot. So I guess we probably should make it. And if we don't, someone else will. And so I guess we should make it and make sure it's safe. I should say, like, also volume manufacturing is extremely difficult and underrated, and we've gotten pretty good at that. So it's also important for the humanoid robot. Like, how do you make the humanoid robot not be super expensive? And
Hi. Thank you for the presentation. And my question will be about scaling of Dojo. And in particular, how do you scale the compute nodes in terms of thermals and power delivery? Because there is only so much heat that you can dispense and only so much power that you can bring to like cluster rack. And how do you plan to scale it? And how do you plan to scale it in multiple data centers?
Sure. You want to take it? Oh, there.
Yeah, hi. I'm Bill. I'm one of the Dojo engineers. So from a thermal standpoint and power standpoint, we've designed it very modular. So what you saw in the compute tile, that will cool the entire tile. So once we hook it up to, it is liquid cooled on both the top and the bottom side. It doesn't need anything else. And so when we talk about clicking these together, once we click it to power and once we click it to cooling, it will be fully powered and fully cooled. And all of that is less than a cubic foot.
yeah, so Tesla has a lot of expertise in power electronics and in cooling. So we took the power electronics expertise from the vehicle powertrain and the sort of the advanced cooling that we developed for the power electronics and for the vehicle, and applied that to the supercomputer. Because as you point out, getting heat out is extremely important. It's just really heat limited. So yeah, so it's funny that like at the compute level, it's operating at less than a volt, which is a very low voltage. There's a lot of amps, so therefore a lot of heat. I squared R is really bites you on the ass.
Hi, my question's also similarly a question of scaling. So it seems like a natural consequence of using, significantly faster training hardware is that you'd be either training models over a lot more data, or you'd be training a lot more complex models, which would be potentially significantly more expensive to run at inference time on the cars. I guess I was wondering like if there was a plan to like also apply Dojo as something that you'd be using like on the self-driving cars, and if so, like, you know, do you foresee additional challenges there?
So as you could see, like Andre's models are not just for cars. Like there are auto labeling models, there are other models that are like beyond car application, but they feed into the car stack. So Dojo will be used for all of those too, not just the car inference part of the training.
Yeah, I mean, the Dojo's first application will be consuming video data for training that would then be run in the inference engine on the car. But, and that I think is an important test to see if it actually is good but is it actually better than GPU cluster or not? But then beyond that, it's basically a generalized neural net training computer. But it's very much optimized to be a neural net. So, you know, CPUs and GPUs, they're not made to be, they're not designed specifically for training neural nets. We've been able to make GPUs especially very efficient for training neural nets, but that was never their design intent. So it's basically GPUs are still essentially running at neural net training in emulation mode. So with Dojo, we're saying like, okay, let's just ASIC the whole thing. Let's just have this thing it's built for one purpose, and that is neural net training. And just generally, any system that is designed for a specific purpose will be better than one that is designed for a general purpose.
Hey, I had a question here. Hi. So you described two separate systems. One was for vision, the other was for planner and control. Does Dojo allow you to train networks that cross that boundary? And second thing is, if you were able to train such networks, would you have the onboard compute capability in the FSD system to be able to run that under your tight latency constraints? Thanks.
Yeah, I think we should be able to train planner networks on Dojo or any GPUs. It's really invariant to the platform. And I think, if anything, once we make this entire thing end-to-end, it will be more efficient than decoding a lot of these intermediate states. So we should be able to run faster if you make the entire thing end-to-end neural networks. We can avoid a lot of decoding of these intermediate states and only decode the essential things required for driving the car.
Yep. Certainly, end-to-endness is the guiding principle behind a lot of the network developments. And over time in the stack, neural networks have taken on more and more functionality. And so we want everything to be trained end-to-end because we see that that works best. But we are building it incrementally. So right now, the interface, there is vector space, and we are consuming it in the planner. But nothing really fundamentally prevents you from actually taking features and eventually fine-tuning end-to-end. So I think that's definitely where this is headed.
And the discovery really is like, what are the right architectures that we need to place in the network blocks to make it amenable to that task? So like Andre described, we can place spatial RNNs to help with the perception problem. And now it's just neural network. So similarly for planning, we need to bake in search and optimization into the network architecture. And once we do that, you should be able to do planning very quickly, similar to C++ algorithms.
喂，好啦，唔好意思啊。由於小弟陣間要開會，咁所以個直播要大家想睇埋啲 Q&A， 我估佢仲有5分鐘 Q&A， 咁可以翻 test 下直播睇。咁最後咧補充翻一啲資料啦，因為佢講超級電腦嘅時候咧，其實佢好平淡咁樣帶過咗嘅。咁其實我之前揾個資料咧，就係佢部超級電腦咧。嗰陣時，呢個係幾時啊？2年前，2021年嘅呢個啟用時間。咁富優係日本嘅嚇，富優電腦咧，佢嗰個速度係尖峰效能係達到1 exaflop 嚇，即係頭先我所講嘅。咁頭先我打咗出嚟啊，1 exaflop，即係啲數字已經係大到我哋平時好少用㗎啦，係講緊幾多兆啊？100億啊！即係100京啊，係啦，100京嘅係啦，我哋冇理解。咁所以佢嗰個電腦呢度富優蟬聯超級電腦計算速度係第2名嘅，咁日本嗰部。咁所以佢除咗車 除咗個 software 之外咧，佢而家嗰個超級電腦咧，其實都係世界頂尖咯。咁所以佢好合理地就係佢諗緊嘅嘢，佢既然而家有個超級電腦可以應用喺嗰個車嘅人工自動駕駛之外，佢仲可以應用喺邊度咧？咁所以佢開發機械人其實都係一個好合理嘅事情嚟嘅。咁另外就係如果大家有興趣去睇一套電影咧，如果你有 on Netflix 嘅話咧，有套戲叫做 Better Than Us 嘅嚇，咁佢嗰個科幻背景，我認為同未來嗰個背景係好似嘅，即係好多嘢係被取代啦。電影係講佢哋有計劃就係所有人40歲退休。咁頭先 Elon Musk 其實 Elon Musk 唔止一次提過㗎啦，佢就話呢個世界將會邁向呢個叫做universal basic income 嚇。呢個字喺邊度嚟咧？就係嚟自烏托邦。烏托邦即係個理想嘅世界。理想嘅世界咧，人類係唔需要做嘢嘅嚇，機械人做嚇。咁人唔做嘢，咁做點點生活啊？咁樣，所以就政府派錢嚇。咁其實唔知挪威定邊個國家係試過政府派錢嘅，但係唔得嘅嚇，因為始終人係要做嘢嘛。一人冇錢係冇動機做生產嚇。咁但係當有 general purpose 嘅，即係啲機械人唔係我哋嗰啲咩即係其實車都有機械人嚟㗎，但係佢唯一嘅功用就係揸車咯，做一件事嘅啫，其他嘢唔識做㗎啦。咁佢頭先講嗰個機械人咧係叫做 general purpose 嘅通用性。咁嗱，呢個通用性咁例如巡邏機械人啊，嗱電影入邊咧就發生嗰啲情節就係性愛機械人啦嚇。咁管家屋企嘅管家啦嚇，咁嗰啲嘢咧佢會幫你斟茶遞水，呢啲最基本嘅嘢就佢幫你做咗咯。咁就係呢個叫做 general purpose。咁搬貨啊、搬重嘢啊嗰啲全部都係啦。咁搬運嘅啲又唔使做啦嚇。咁我哋會計嗰啲就俾軟件做啦。咁所以呢個就係一個即係科幻情節嘅嘢就做緊咯。咁個超級電腦其實咩嚟咧？其實你想象就係即係咁嘅嚇。佢頭先冇好具體睇到相嚇。咁佢入邊頭先拆開嗰啲咧就一嚿嚿晶片對落嚟。呢個就係內地嘅。咁都係 top 3嗰啲超級電腦啦。咁內地嗰個就叫做神威電腦。咁都係超級電腦嚟嘅，咁所以大家要理解就係話佢即係世界頂尖嘅，佢而家一個超級電腦係世界頂尖咯。咁同埋佢成個主題就係佢因為好多人質疑佢哋嗰個移除咗個雷達之後咧，其實美國嗰邊有嗰個咩 NTUS 中文我唔記得叫咩，即係一個安全揸車嘅協會啦。佢就成日將啲汽車評分安唔安全嗰啲咧。香港都好似有嘅，我唔記得叫咩名。咁佢哋對 Tesla 移除咗個雷達係表示擔心嘅。咁所以佢某程度佢個 presentation 頭先佢好強調就係話，佢單用8個鏡頭，佢都模擬到一個立體嘅效果。其實當中有啲 slide 咧，我係之前嘅佢嗰個 Andrew Karpathy 即係嗰個 AI team lead，其實佢喺其他地方 present 嘅時候都有出現過嗰啲 slide 嘅。不過今次呢個我冇諗過係咁 technical 咯，因為佢今次呢個會議係純粹係攞嚟請人用嘅，所以你見到在場啲人問啲問題都好深啊，因為嗰班可能全部都係啲 AI 相關嘅人員咯。咁所以佢今次嘅目的好明顯就係佢要吸納最頂尖嘅 AI 人才咯。唔係讀優啊咁啊，富岳啊，係啊，富岳電腦啱唔啱啊？鱷魚個鱷係啦，富岳電腦係啦嗱，今次嗰個直播嚟到呢度啦。咁我下個星期都未必有時間。下次啊，因為原本我有條影片係原本就係錄呢個 topic 嘅，咁啊原本等咁而家 FSD 9.0出咗啦，大家可以 search FSD 9.1，你上網會揾到好多去自動駕駛嗰啲影片噶啦。咁我睇下會唔會喺未來2個星期內會整理到今次呢個 AI Day 嘅影片啦。好啦，今次嘅分享嚟到呢度啦，拜拜。